Let's keep on going with this one. The reaction below has known to proceed at 85% of yield of SO2. Be careful here because here they're not asking for the yield. They're giving you the percentage of yield. But why are they giving you the percentage of yield? What are they asking for? Let's check if it's balanced. For, I think it was 10 sulfur 5 and 5. Yeah, 20 oxygen, 10 plus 10, 20. So how many grams of P4S5 must be burned? They're asking for this one, right? To produce 50 grams of SO2. 50 grams of SO2. Now listen and be careful here. Everybody got the same mistake. Most of you. And it's because if they're giving you the 85% 0.3% of yield of SO2. What are they giving you? The actual yield. Actual yield. Remember, that's usually what they give me. And they're asking, right, to calculate the amount burned. But can you take the actual yield to calculate that? No, you have to take the theoretical yield. So it's gonna be remember the percentage of yield, 85.3 is gonna be the actual yield divided by theoretical by 100. In other words, let's say that you're going to react this to obtain SO2 and you want to know the amount. You need to have 50 grams of SO2. But you know that the reaction proceeds at 85.3%. Would you make burn P4S5 to just make 50 if you know you're going to produce less? Because if this is the percentage of yield, after the experiment, you're going to end up with less than 50. So what do you need to do? Base your calculation. How much do I need to burn, right, to theoretically, supposedly produce more than 50, but if 85% of that 50, of that number would be 50. In other words, you have to obtain, theoretically, you're supposed to get more. Okay, remember the 85.3% is just a percentage less than 100 of what you're really gonna get. So 50 would be the actual yield, and it's 85.3% equals the actual yield, which is 50. So you really want to get after the experiment 50 grams. So if the percentage is 83, how much would you theoretical need to get? So that way you can calculate how much do you need to burn. Not all the amount that you're supposed to get of SO2 would be really obtained. It's gonna be a little bit less, so you need to put more. So how much would be the theoretical yield? Would be, so it would be the SO2 calculated, right? Suppose, theoretical, that's the word theoretical, 50.0 divided by 85.53 multiplied by 100. And by the way, this is divided by 0.853 or 50.0 grams divided by 0.853, and that's the theoretical, and it gives you this gives you 50 divided by 85 by 0.85, 853 equals 58.61 grams. Now we're going to do the calculations with the equation and the stoichiometry, what is called 58.61665 grams. Now with these numbers, right, we're going to convert it, the flow chart, we're going to convert it 2 moles of SO2, and we're going to be able to calculate how many moles and then grams of P4S5. So if you have here, hold on for a second, I'm going to have to put pause because if not, this video is going to. So having here, I wrote the equation. So what do you need to do now? Well, you need to find out the moles of SO2 from the grams because you're going to have to prepare. You're going to have to calculate to obtain 58.61. So that way, after you finish the experiment, you get a total of 50, knowing the percentage of yield. So 58, I divided by the molar mass, so we got the SO2 in grams. We divided by molar mass of SO2 to get the moles of SO2, moles SO2. Then we do the ratio 5 to 1. We get the moles of P4S5, and they're asking for the grams, if I remember well. Yeah. And then you have to multiply it by the molar mass of P4, molar mass of P4S5. I'm going to do something to get the grams of P4S5 that you need to burn. I'm going to put it in pause and calculate the molar mass that we all know, so that way I don't waste time doing it during the video. Okay, I already calculated the molar mass. So now what I need to do, we need to calculate first the moles of SO2, right? And then to do the stoichiometry ratio. So the moles of SO2 would be equal to, let's look at the molar mass, would be equal to the 58.61665 that I got here. 58.61665 that I got here, grams, divided by the molar mass of SO2 that I calculate already, and I'm going to show you anyway, okay? And it's going to be 1 sulfur, 32.07, plus twice the 15.994, it gives me 64.0688. 64.0688 grams per moles gives me moles. So this is going to be the moles of SO2 is going to be equal to 58.61665 divided by 64.0688 equals 0.9149 moles. And then now what do we have to do? The stoichiometry ratio. So it's going to be 9149. So here again, 0.9149 moles. Okay, and C is a 1 to 5, and then X would be here. So it's going to be 1 over X, 1 mole over X, and 5 over 9149. So here would be the stoichiometry. 1 mole of the P4S5 will produce 5 moles of SO2 according to the chemical reaction. 5 was SO2. And beside, if you have a doubt, just do what I mean, up the equation and down the calculations on the bottom. So it's gonna be X because this is what we want, and here would go 0.9149 moles. And this is moles, SO2 moles. And this is SO2 moles too. So this and this cancels out, right? And you got X up, it would be 0.9149 multiplied by 1 mole of P4S5 divided by 5. And this is gonna be 0.18298 moles of tetraphosphoro pentasulfide. Now, this is moles and they're asking for grams. So what is the next step? Multiply by the molar mass of the P4S5. And it is 284.2448. So we multiply 2448 grams per moles, and that is gonna give us 52 grams, 52.011 grams. And how many sig figs are we talking about here? Let's look at the question. It's gonna be 3. Exactly 52.0 grams. And that's what we got. Okay. 52.0 to 3 sig figs grams. Okay, let's do the next one. And the next one is, they're asking for the identity of this metal. Okay? And you have a metal carbonate, which with heat decompose and the metal oxide plus CO2. Now you have to be sure here that when you have a chemical reaction like this, right? Nothing is going to go anywhere else. The metal is going to come from here. The carbon is going to come from the CO3. One oxygen comes from here and the other two from here. So, and they're giving you the total, they're giving you the grams of the MCO3, right? Which is going to be 1.056. And they're giving you the grams of CO2. So the grams of CO2. Wow, how can we start? Because we can't find moles of the metal because we don't have the identity of the metal. Okay, so why don't we do something? Why don't we find first the moles of CO2? Because we can do it. At least we have something to start working with. 12 plus 2 times 15.9994, and this is 12.011. You know how to do it. I want you to do it, but in the video, I'm just going to do it in the calculator. I don't want you to do it on the calculator because I need to see just in case you made a mistake. Plus, it's going to be 12.011 plus twice 15.9994. It's going to be 44.00. The molar mass of CO2 is going to be 44.0098 grams per mole. So here you got 0.376 grams. So we can calculate the moles of CO2. And what are we going to do with that? I'll tell you what we're going to do with that. You'll see. It's going to be what? It's going to be 0.376 grams divided by the molar mass of the CO2, which is 44.0098 grams per moles. So now you can find out the moles of CO2. And it's going to be it's going to be 0.0085435. As I said, like that. 44, because we're dropping the 5 something, so it's 44. 44 moles. Now, there's something you need to know on the concept. If you have 1 mole here of CO2, isn't it the same ratio 1 to 1? It's 1 to 1. 1 mole of the metal oxide gives you 1 mole of CO2. So if you're going to be producing 0.008544 moles, how many moles did you add of the MCO3? The same. So the number of moles of MCO3 is going to be equal to the number of moles of CO2, which is going to be 0.008544 moles. Now you got this. Good. But you still don't have the metal. But you get the grams too, right? You have the grams or not? Yes. And the moles, you know that the moles, number of moles of the MCO3 would be equal to the grams which you have, okay? The grams divided of the MCO3 divided by the molar mass of the MCO3. But you don't have it, right? So what do? You go ahead and let's put the molar mass. Let's take it to top. So the molar mass of CO3, I cross multiply, is going to be grams of MCO3 divided by the number of moles, right, of MCO3. Some students like to see it in step or not. Now you know that the molar mass of CO3, any molar mass of any compound, is going to be the molar mass of the CO3 is going to be equal to the molar mass of the metal, right, of M, plus 1 time by the carbon, grams per moles, plus 3 times the oxygen. Yes or no? In other words, this would be the CO3 molar mass. So this is going to be, right, the molar mass is going to be M. Let's leave it as M or X. Let's use X. M. M plus, on the molar mass this side, I'm going to solve it for this. I'm going to go ahead and add 12 plus 3 times the oxygen, 0.9994, multiplied by 3, multiplied by 3, plus 12.011, that gives me, impossible, 12.011 plus 3 times 15.9994, okay, equals 60.0092. And that is going to give me the grams, which we have. The grams is 1.056 of the whole metal. And the moles are going to be 0.0854 moles. So 1.056 grams divided by the moles you have in this sample that we calculate from the CO2, which is 0.0088544. 44 grams. I'm sorry, moles. Moles. And this is that we calculate grams per mole. Now, if you solve it for M, so we're gonna go ahead and solve it for M. We're gonna subtract 60.0092 grams on both sides. And here we have to do this division, 92 grams per moles. So this is gonna give you 1.056 divided by 0.008544. That gives you 123.5956 grams per mole. So here, this is gone, and this would be M is equal to 123.5956 grams per moles minus 60.0092 grams per moles. It's going to give me 63, the molar mass of the metal, the atomic weight, 63.5863 grams per mole. If you look at your periodic table, the most closest one to 63 is going to be 63.546, right? We're on target there. And it's going to be copper. Okay, so the answer is B. Let's go with number 5. Given a sample of liquid hydrocarbon, again, X and Y, plus O2, because it's going to burn combustion, it's going to give you CO2 plus H2O. Do you remember we did this in class? Plus H2O. So you got 17 grams of CO2. CO2 is 44. The molar mass of CO2 is, and we have it up here, is 44.0098. It's going to be 44.0098 grams per mole. And the molar mass, of course, we're going to have to find out moles. And the molar mass of water is going to be 18.015 grams per mole. So let's first start finding out the moles of CO2 and the moles of water. Okay, so the moles of CO2 would be the grams given, which is 17.01. So the moles of CO2 would be equal to 17.0 grams divided by 44.0098 grams per mole. So this and this cancels out. And this is going to be this is going to be equal to 17.0 divided by 44.0098 equals 0.3. Yeah, to make sure I got it right. Yeah, 0.386. Let's keep the decimal because we're going to do empirical. 2, 7, 77602. Now the moles of water would be equal to the grams 464 divided by 18 point the molar mass of water grams per mole. If you don't believe me, just look at that and calculate it, and it's gonna be 4.64 divided by 18.015 equals 0.22575631142 moles. Now this is the part that it's a conceptual part. Very important. It's a concept. For every mole of CO2, how many moles of carbon you're going to have? One, because it's a 1-to-1 ratio. Remember, we multiply the moles of molecule to find out the moles of atom. We multiply by the subscript. So that means that the moles of CO2 are going to be equal to the moles of carbon. Okay? And the moles of carbon are not coming from anywhere else than from the hydrocarbon. The same thing with the hydrogen here. The hydrogen, but the difference here is that if you multiply to find out the moles of hydrogen, right? How many moles of hydrogen, atoms of hydrogen, how many moles of hydrogen you have in 1 mole of water? You have to multiply the moles of molecule of water by 2 because it's the moles of molecules to moles of atom, and you multiply by the subscript. Now it's gonna be right twice this number, 0.2575631142. It's an indirect way. This is kind of an indirect way of doing what we used to do with other empiricals. And this is going to be by 2 is going to be 0. I mean, you get it from CO2, but you're doing the same thing that we do empirical because now that you got the moles of each one, then you divide it by the small ratio. Remember when we got the grams of carbon and hydrogen in another one? We just have to assume 100 grams. If we got a percentage, it's exactly the same. The only difference is that we're using a chemical reaction, and instead of giving you directly the carbon and hydrogen percentage of composition or the carbon and hydrogen grams, they're giving you the grams of CO2 and water. But you know by the concept that of molecules to atoms, you have to multiply by the subscript. You know then what is the moles of carbon and hydrogen. And once you know it, you also know by stoichiometry that it would be the same as the moles of carbon in the hydrocarbon and hydrogen there. So it's going to be 0.5126 26284 moles. Now let's make it clear here for a second. And is that once you got this, remember, okay, let me write down, then the moles of carbon are going to be equal, right, to the CO2, which is 0.38 6277602 moles. So now remember what we used to do with empirical. Once we get the moles of each one of carbon and hydrogen, we have to divide it by the smallest one to get the ratio. And the smaller one is the carbon, 0.386277602 moles. And then we get the ratio. And so here, carbon 1. How about this one? You divide 0.5155 by 0.386277602 moles. Let's see how much it gives us. So it's going to be divided by 0.386277602. And I know why some of you got it wrong. Because it's going to give you 1.33. Again, I say it again and again and again. Do you round this? No. My tongue is gonna fall. No. And that's, I think, the majority of the mistake. This is 1/3 2, or you multiply by 3 and you know you get rid of it. 1.3333 is 1/3. So you need to multiply both by 3 and both by 3. So this and this cancels out, right? This is 1/3. This is gonna be 4/3. Yeah, 4/3. Because we're gonna 3 is 1, then 4/3. And it's gonna be 4, and this is gonna be 3, the carbon. So what is the empirical formula? C3H4. Let's see, because maybe I got it wrong. C3H4. Here it is. The problem you probably had is that you rounded here. Here. 1.333, you know you multiply by 3. Just learn it by memory. 993. I remember when I got to the graduate degree, the test, the ERE asked me those questions about the fraction. You need to know that. And if you want to do a graduate degree, you need to know this math. So this is going to be by 3. Okay? And that's why. And then we have to multiply them. Or either you put it as a fraction, 4/3, or you know you multiply by 3, and this is going to give you kind of 3 by 3, 9, which is 4. So you got C3H4. I'm going to stop here, and I'm not going to post it until the last ones that are supposed to take the quiz. Then I'll start it posting. When I started posting, I'm not going to give opportunity to take the quiz late. 5.